Hello everyone, today we're going to take a look at the Rao-Blackwell theorem, and that is pretty interesting in statistics when it comes to looking for the UMVU estimators, meaning the uniformly minimum variance unbiased estimator. So as the name says, we're looking for an estimator whose variance, let's write a few things, whose variance is uniformly minimum, and it has to be unbiased. So those are some ingredients that we're going to see in today's theorem. Now, before we get started, let me actually just write the theorem down, and then we'll proceed with the proof and a few observations. This is what I like to do. So as usual, when it comes to mathematical statistics, we got our. I like to write it this way. I like to write. It might be not the best way to write it. So by this I mean a random sample generated by this probability distribution function. CDF, and with this time we're gonna write it this way, the PDF, whether that is discrete or continuous, doesn't matter. Okay, and obviously I'm emphasizing the fact that we are in a paramedical, let's say, what can I say, a paramedical setting. So we are actually doing some so we are investigating on this parameter theta, and as usual, theta can be a scalar or a vector. So you can think about theta as an element in capital theta, which is a subset of RK. Now, so I'm gonna write this one here. So this is setting. So what we're looking for is, what we need is a statistic that has to be, sufficient statistic. So instead of being hyper formal, let's just write we need. Let me highlight it. Some colors here and there. Okay, sufficient statistic, and for theta, and actually let's just do it this way. And as we said, we need an unbiased estimator of what? Obviously of our parameter theta. Now at this point what we get is that by defining this new object, Vn Tn, could have a better name, but that's the way I was taught, as the conditional expectation of Vn condition on Tn. So what we get is, then, if we have these two ingredients, is 1, unbiased, 2, uniformly minimum variance, which actually, let me just write it, and then we'll proceed with some observations. The way I see it, if you don't really make observation on your theorems, your properties, theorems are properties at the end of the day, you're not really trying to understand what you're doing. And then it is a function of a sufficient statistic, and obviously by sufficient statistic we mean a statistic whose PDF does not depend, condition PDF whose condition PDF does not depend on the parameter. Okay, right? So that's the theorem, that's a claim. We're going to do the proof in just a second. As I said here, as you can see already, this one follows literally by definition, as the if you're familiar with some probability theory, which is not too advanced, this object right here is a function of Tn, right? Hence, 3 basically follows by definition. It's already, I like to joke with my colleagues. I usually say by definition, but it actually is. The only thing you can do is you can show what this thing is, this object is, and actually that way you see even more clearly that it is a function of Tn, hence a function of a sufficient statistic. And basically what we're saying here is, if we have a sufficient statistic and an unbiased estimator, if we take the expectation of the unbiased estimator and we condition it, then we still have an unbiased estimator, so the unbiasedness is preserved. Not only that, but then we have a better estimator in terms of variance, so in terms of efficiency, but we do not have a an efficient estimator. This implication, nope, we don't have that. However, we do get a better estimator. Now, the proof is extremely simple. It just follows from probability theory properties. Now, and these 2 properties are, so recall, my professor used to write memo, but I think this is more an Italian thing. A mem, might make sense in English too, but that's not important. What is important is we need to remind ourselves that the expectation, and I like to here use theta, just to remember we are in a parametric setting. This is equal to the conditional expectation, to the expectation of the conditional expectation. This is simple to prove. This, once again, is a function of y. You write this as a function of y, right? I use the integral. The integral can be meant as, the expectation can either be an integral or a sum, depends on where you are. Many times I'm used to use an integral, even though we are in a discrete case. It just at the end of the day, is mainly just a notation. Who cares? That's when you know how you've done it a lot of times. Yeah, and then just you rewrite this as what it actually is, and the thesis, the claim follows very easily. And obviously, another thing that is very used is variance decomposition formula, which I will remind you is this guy right here. So it's the variance of the conditional expectation, right, plus the expectation of the conditional variance. Now, if I ever forget theta, it's not important, but it's always there. Just if you're wondering, yeah, of the expectation of the conditional variance. Now, at this point, we literally have the claim. Let me show you. So, consider, I'll just keep on, consider x equal to, obviously, Vn, and y, Tn. At this point, so let's first show 1, so the unbiasedness. Okay. At this point, 1 follows from what? New page. Okay, so 1 follows from the fact, from, let's call this A and B, from A. Okay, So we have the expectation of Vn is equal to the expectation of the conditional expectation of what? Of Vn Tn, right? So we need to, the claim is this object right here is unbiased, right? But what is this? We know that Vn is an unbiased estimator. So this is equal to theta. This is an estimate, we're trying to estimate theta once again. So this would be equal to theta, right? So the expectation of our new object, it's equal to the parameter. Hence, it's unbiased. Once again, by definition. Okay, now quickly, because I'm taking too long as usual, 2 follows from B. So the variance of, once again, Vn is equal to the variance of the conditional expectation plus the expectation of the conditional variance, Vn condition to Tn, right? Awesome. Now, let's write theta, because if I start it, I gotta finish it. Awesome. So, what we're trying to prove is that the variance of our new estimator is less than the variance of the sufficient statistic, right? Sorry, as I said it, I understand that the variance of a statistic does not make sense. So I don't know why I wrote Tn. Awesome. That's when you know you learn things, right? When you I literally said the variance of a statistic, and I'm like, what am I saying? Very good. But yeah, I'm human too, so I make mistakes. Okay, so now, so basically we're trying to prove this is less, or I mean greater or equal than the variance of our new estimator, right? Okay, but this is the variance of estimator, right? So this is the variance. Let me clean up a few things. So I'll just claim, because that's the thing, when you're doing on a tablet or whatever, not on a piece of paper, you don't have the clear picture of what you're actually trying to prove, which is why I like to do it on paper, to be honest. Okay, I cannot write anymore. Okay, right, that's a claim. Awesome, but this is equal to the Tn. This is a variance. This is a non-negative function of Tn, right? Perfect. The expectation of a non-negative function is non-negative. And this comes from mainly measure theory. Hence, it's greater, right? This, they're equal. If you subtract, if you bring this on this side, you're subtracting, it's minus something positive. This one hence is less or equal than this quantity, hence the thesis. Awesome, so this was Rao-Blackwell. Any questions, any mistakes apart from this one? Pretty big, but yeah, sorry about that. Let me know down in the comments, and I will see you in the next video. Thank you.